Okay, so let's get started. Welcome back from lunch. My name is Alena, and this is my colleague Peter, and we both work as developers at Avast. So first, a little bit more about Avast. So Avast is an antivirus company. So we have antivirus for like Windows, Mac, and mobile. And our goal is actually to protect our users against malware and other kinds of threats. What you might not know about Avast is that it's actually originally a company from Czech Republic. It's more than 25 years old, and when I joined Avast, it was like 7 years ago. There was like 120 people, so it was still quite small company. But right now there's 2,000 people, so we grew a lot in the past few years. And we grew especially a lot last year when we acquired a much bigger company called AVG. So about our presentation, first I'm going to talk about Threat Labs. That's part of the company that me and Peter are from. Then we are going to briefly describe a project that's called CyberCapture. This was actually our first biggest project, a bigger project where we used microservices. So we will demonstrate some microservices stuff on this project. And the rest of the talk, we're going to talk about microservices. We're going to cover development, deployment, and running microservices in production. So let's start with Threat Labs. From my point of view, Threat Labs is like the heart of the company because that's where the security is actually made. So in Threat Labs, there are people like researchers, malware analysts, reverse engineers, or also developers like me and Peter, who help to automate stuff for these other guys or create some tools for them. So I assume that most people here doesn't know much about antivirus industry, so I'm going to cover that very briefly. So if you want to actually make an antivirus, what you need in the beginning is like some source of suspicious or malicious files. So if there's a new threat in the wild, you want to have some source that sends you some files describing this threat. Then you just feed these files to malware analysts. Malware analyst just analyzes them and creates detection for these files or for these threats. You will release this detection to your users, and your users are protected, so everyone's happy. But there's actually one problem, and this wouldn't work for Avast right now. And that's mainly because we have like 400 million users worldwide. So we have like 260 million users on desktop computers and 180 million users on mobile phones. So to put that into even more numbers, every day we see almost 1 billion files. That's like 0.5 terabyte of data. And we see like 100 million detection hits in the wild. So to cover all this, you would need like really a lot of malware analysts to do this work. So actually many years ago, we realized that this model just doesn't scale. So what we did is that we basically automated everything that can be automated. And that's a project called Scavenger. That's actually a project that our team is working on for many, many years. And it creates most of the detections. Okay, and there's one more problem with this picture, and that's actually the gap on the top. So for some new threat in the wild, it might be important to get the file first. So it's not that easy to protect the user if you don't have the file first. So we actually wanted to close the gap. And so we were thinking, like, how can we protect even the first user? And that's a project, one of the projects that cover this is called CyberCapture. So now I'm going to briefly describe the project CyberCapture. So the CyberCapture story starts on the computer of our user. the user usually downloads some file, and this file is suspicious. We actually don't know whether it's malicious or whether it's clean, because there's just limited things that we can do directly on the computer. So what we do is that we lock the file for the user, and we submit the file to the cloud. In the cloud, we perform some analysis on these files, and when the analysis is done, we return the result back to the client. So we tell him whether the file was malicious or whether it was clean. And if it was malicious, we just remove it from the computer. So this is the project. Actually, for us, like for our team, this is the most important part, because that was the part that we were working on. That's the part where the analysis happens. So there were some requirements for the project. First, we had to finish it in 3 months, which is not a lot. Then, for clean files, it was really important that the result was returned very fast. Because if you're, for example, looking at some non-malicious Word document, and Avast says that it's malicious and that it wants to lock the file, you want to unlock the file as fast as possible. So it's really important that the clean analysis is returned very fast. For malware files, we can analyze them longer for up to 6 hours. And also, it's very important that this system runs like all the time.
So I'd like to talk a little bit about how we started implementing this system and provide a little bit of context first. So in the beginning, we had this Scavenger system we already talked about, and it is a really huge and powerful system right now, but it has been in development for many, many years, right? And it's only natural that we started to pretty soon see the shortcomings we would encounter if we wanted to build this new cyber capture thing on top of it. It was really not that easy to change, because it became over the years it became this mess of dependencies. We were hard at work at untangling those, but still I would call the system pretty much a good example of a legacy system. Deployment of that system took close to an hour or so, which is not that great. At that time, it was pretty much tied to Windows, because it was written in single language, which was C# and .NET, and we could only scale it as a whole, which was a bad thing, because since the system has so many responsibilities, we would like to be more flexible in scaling the various parts of the whole thing. And it turns out that microservices promises to solve all these problems for you magically, right? So of course we wanted all that, so we jumped headfirst into it. And even though we had a lot of unanswered questions, we felt, I would say, honestly, fairly confident we could pull this off. We had a pretty mature team. We felt that we had already been doing most of the stuff right, like we were big on automation already. CI, we did code reviews, we were testing stuff pretty well, I would say. So we gifted ourselves with the opportunity to design the new system from the ground up, which is a rare opportunity, usually. So very briefly, I'd like to go into how the data flows through all our services. The pipeline goes left to right, okay? So in the beginning, we start with receiving the physical file from your desktop machine. And along with that, we also receive little pieces of metadata which provide more context about the file. I'll give you one example. For example, the URL your file was downloaded from is a very essential piece of information for us. And since those two pieces of data might arrive at different times, we need to join them together. We approach this as pretty much as a stream of data, which we join. While we're at it, we also filter some stuff out, especially files that are already under analysis or that we just don't want to deal with because they're of different types, etc. Then we schedule all those files for analysis by so-called analysis boxes. It's a pretty funny name, but it's pretty much the most important thing in the system. And I'll give you a few examples of what those services perform. For instance, we run your file in sandbox, right, in virtual machines, and watch how it behaves in the system. We watch for things such as how quickly the file spreads among the user base, which is a thing that changes over time very quickly, usually. If we are hit by ransomware stuff, then the curve is pretty wild, usually. So we need to perform all those analyses frequently and rerun them because the environment changes constantly. Malware is pretty dynamic stuff. And every time we have a piece of analysis ready from one of those services, it is then passed on to service, so-called decision maker, which is responsible for aggregating all that stuff and making a solid decision. Then we pass the information on to a system that is pretty much external to our team, and that system is responsible for notifying the user. It unlocks the file on your desktop machine, etc. So we were thinking how to implement this the best way. We settled on, after some discussion, that an event-driven system would be pretty much probably the best thing for us. I'll give you one example what I mean by event-driven in this context. So imagine you get all those analysis boxes, and there are lots of them. And every time one of those boxes has a result ready, it just emits an event. And it is up to other services in the system to listen to that event if they find it interesting to them. So for example, what we do is we model our events as JSON documents. That's not that important, but every event has a standardized name and a format. And we knew from the very beginning that the analysis boxes are going to be the exact place where we would need most flexibility, right? Because we have a huge research team which is always busy coming up with new ways to write analysis around files. And we wanted to give them the freedom to participate in the system without us having to implement everything. So they can just come in, plug in their service, and as long as they consume the right event and emit the right events, they can be easily integrated into the process. What is great about this is that every time they plug in a new service, a new analysis box, the data it produces gets automatically stored somewhere, so it makes it super easy for them to test drive new analysis. We usually run it for several days or weeks on real-time or real-world data, and only if we see fit we adjust the decision-making process to take the new analysis into account. Yeah. So a few weeks into the project, threat messages start flowing through the system, and what I think was really essential for us from the very beginning was to be trying to cover the whole flow end-to-end as soon as possible. This may seem pretty obvious, but I can't really stress enough how important this was for us, because we didn't do that soon enough, I would say. We should have pushed harder for this, and it would have saved us some oversights we have committed in the initial very short design phase. We use RabbitMQ to facilitate messaging in our system. It's pretty popular. I think most of you are probably familiar with it. It has few very simple concepts, and this is how we use it in our system. It's pretty much a very typical publisher-subscriber kind of thing. Nothing fancy and nothing that interesting. But for those who are not familiar, the publisher, the service which emits messages, simply publishes a message to a given exchange, and it is routed to a particular queue via rules, simply by simple routing key match. And on the other side, you get another service, which usually runs in multiple services and consumes the messages from the top of the queue. One thing about this, again, fairly obvious, but it is really important for us, that this makes workload distribution very easy, because you just spin up multiple instances and you have multiple instancing done for you pretty much for free. One thing I would like to stress here is that we never fiddle with the administration UI manually. We do all the setup of RabbitMQ objects programmatically. That's very important. And in our case, it's the responsibility of the consumer application to specify what it needs to be present in the system. And every consumer application creates its own queue and specifies from what exchange should it be routed. So yeah, the green line, that's pretty much the happy part, right? The service processes message, says everything's okay, and all good. But usually you have to deal with failure more often than we would prefer. And it turns out that this is something that we struggled pretty mightily, especially in the beginning, because there are so many kinds of failures. It's crazy. Sometimes your service would receive completely wrong messages. You would expect a JSON document and some other service, which of course has a bug in it, because it's not that well tested, sends you some total garbage. So what do you do with that? In our case, we just log it and forget about it, because there's not much we can do to recover from that. There are more subtle ways of invalid messages flowing through the system. I'll give you one example of this. Pretty much everything we have in our system is modeled around files, right? So that becomes our correlation ID. The file hash, the SHA-256, is our correlation ID we are sending everywhere. And it would just so happen sometimes that a bug in some upstream service, which we wouldn't expect, causes the thing that you start receiving complete bullshit. Some of the kind of messages you can process right now can be even more subtle. For example, it manifests itself only for a certain subset of data. So here it is very useful to use a messaging system, because what we do here is that we just put the message back to the queue, to be more specific, to the end of the queue. We let other messages to bubble up and be processed, and in the meantime we hopefully go fix the bug in the service. So this is something where messaging helps a great deal. It became fairly obvious to us, very clear, that visualizing the whole flow in the system, especially when you have multiple services, each of them creating many objects in RabbitMQ, it's very easy to lose track of who's communicating with whom and how events are flowing through the system. So we started with a simple whiteboard. It worked very well for us initially, but that doesn't scale obviously at all. So we ended up using just some simple drawing tool, anything that can draw shapes basically, and where people can collaborate on. That's super important. But we didn't need any fancy modeling tools for that. So yeah, that was pretty easy. One thing that we found ourselves doing constantly was talking about stuff, right? Sometimes I would say even a little too much. One of the topics we are talking all the time about was service size, right? That's like the classic theme of microservices. Everyone's talking about the right service size. And we did have some endless discussions about it. In the end, we settled on a very simple way to think about this. And that is in terms of time, right? So we try asking ourselves questions such as, will you be able to write the service in 2 weeks, in 1 week, what have you? Will a newcomer will be able to understand the code in 2 hours, 1 hour? Obviously, there are no hard rules around this, but this has seemed to work pretty well for us. But one rule we do try to stick to pretty strictly revolves around storage, okay? So we try to keep our services stateless, if possible. It's not always doable, obviously, because sometimes you just need to keep state somewhere. And one rule that we are very strict about is that services are never allowed to touch each other's data, right? They never access their databases directly, always through an API. That is super important because, and we learned this the hard way. Once we broke our own rules, and I would never ever do that again, because you just very quickly find yourself in a tough spot when you can't change anything because someone is tied to the internals of your service. It's like a simple rule of encapsulation, but yeah, we broke it once, and it was a mistake. We also do have some user interface. even though I'd say it's pretty simplistic because that's what was needed in that case. And we had been talking about how to do that the best way. And in the end, we settled with an approach that's super simple. We have a separate service for that, and that service just keeps track of the interesting events which are happening in the system. And it keeps a separate representation of the data in such a form that is well suited for the UI. Obviously, that means we duplicate some of the data, which is sitting over other services, but it works well for us. Then we have a very simple JavaScript app and an API that wraps the storage, and yeah, it works pretty well. But I would say there is one thing to look out for here, and that is, since service of such kind tends to aggregate the data from the whole system, because people want to see all the stuff in one place, right? It makes it very tempting for everyone to treat this particular service as the one go-to place when they want to ask some stuff in the system. So it's very important to communicate that the responsibility of this service is solely for the UI purposes and can break because of UI needs.
Okay, so another thing that people discuss quite often is like that if you're doing microservices, you can actually choose the language that you want to write your service in, like that you can choose the right tool for the job. We actually wanted to take advantage of this too, because by the time that we started with the cyber capture project, our team was really diverse. We were like 8 people, and half of the team was writing their stuff in Perl, and half of the team was doing Scala programming. And if we built cyber capture as a big monolith, there was actually no easy way how these two groups can cooperate on this together. So thanks to microservices, we could have built half of the services in Perl and half of the services in Scala. Also, we can't forget about Python, because Python is like the most commonly used language in threat labs, especially in the research department. And we wanted them to be able to extend the system. So 3 languages, that seems like, it seems okay, but from my point of view, it's like 2 more than it should have been. Because like if you have, what's really important when you're doing microservices is to enforce some conventions, like do every service in some standard way. We actually failed this a lot, so we ended up like some weeks into the development, we ended up with, let's say, 10 services, and every service was logging a little bit differently. Every service was monitoring the same stuff, but the keys in the monitoring were a little bit different. We had like 5 different HTTP clients. We had like different JSON parsing and different error handling. And you really don't want that. So it's really important to enforce some conventions. And if you have 3 languages that the whole system is written in, you basically have to do everything 3 times. So what we actually, how we started to make this better is that for the Scala applications, we basically defined the whole stack. So we actually started with a Confluence page, which is like the simplest thing that you can do. So we defined everything from how the project should be structured, how it should be built, how it should be deployed, and this kind of stuff. So if you have your services written in Perl and Python too, so you have to do this 3 times for every language. Yeah, so having a Confluence page is actually a nice start, but it's not an ideal solution, and we are aware of it. So for us, the ideal solution would be to have an actual boilerplate application. So every time you start a new service, you just have this boilerplate ready for you, and all the conventions are already in that boilerplate. So that's the easiest way. So this is just some examples from the Scala stack page. So we agreed that we're going to build our projects using Gradle. We agreed that we're going to build it in the last version of Scala. We for configuring the applications, we use typesafe config. We use Scala style and Scala formatter. This is really important because you want your code across all services to be formatted and to look in the same way. For JSON parsing, we use circ, and all our services expose the status endpoint, and we actually use this endpoint for health checks. So if you actually do all this work and you do all your microservices in some standard way, it actually enables you to do many cool stuff. One of the stuff that it enables you is to scaffold the whole build pipeline. So in Avast, we use TeamCity. I don't know whether you know TeamCity, but TeamCity is like Jenkins, only nicer and more expensive. Yeah, so in the last versions of TeamCity, they've added a feature that enables you to define the build pipeline using Kotlin. There's a similar feature in Jenkins. I think you just write it in Groovy. So we have the whole build pipeline defined in Kotlin. Wherever we have a new microservice, we just add one line to a Kotlin configuration file, and that's it.
Is it okay? So I'd like to talk about deployment for a little bit. And to explain how why exactly we went that way we went, I have to first provide a little bit context how it was traditionally done and how it still is done in Avast in many aspects. So traditionally, when you wanted to deploy an app somewhere, you need to go to the system engineering department and ask them for a VM. Okay, so they spin up a virtual machine somewhere, you state the dependencies you need to have in that particular machine, and that team provides you with a pretty good tool to deploy stuff into that VM. But at the same time, we were looking at, especially in the beginning of our project, we were looking at releasing like tens of services a week. Okay, so it was obvious very quickly that this was not a good approach for us. And yeah, at the time, we had already been using Docker for local development, and it was only natural that we wanted to take the next step and start using Docker in production as well. We kind of waited until the hype settles over Docker and decided to build our own internal cloud, which is built on two open source projects, Mesos and Marathon. One of them is covered by Apache. I think it's Apache Mesos, and together they provide the basis for our internal cloud. Mesos, in very simple terms, you could say that it abstracts away resources, right? It makes lots of machines look like one piece of hardware. It's got some great features such as direct container support, and then Marathon can build on top of that. And it is the orchestration platform which provides stuff such as scaling and load balancing. It also has a nice user interface where you can examine what's going on in the system. Nowadays, you've got all those cool projects such as Kubernetes and Aurora, what have you. There are tons of cool projects which deal with container orchestration. Some of them already in the cloud, but we had started these efforts actually a little bit before, even before the CyberCapture project started. And at that time, we felt fairly confident that Mesos and Marathon was the best thing available at the time, because it was the most battle tested, and it seems to work pretty well for us. But we had to build it ourselves in our team, and that was just because we were able to do it just because we happened to have one or two guys on our team who were pretty good at that stuff. So yeah, what was very surprising for us that the utilization of resources in the cloud was pretty cool. All the analysis runs happily on just 4 nodes, although pretty powerful ones. And we're currently running over 100 applications. I mean, not all of them are tied to the CyberCapture project, but well over 100 applications, and most of them are run in many instances. So this is how it looks like from the developer perspective. You may know Kubernetes command line interface. This is something similar, but we do it via an API. So you start out with a simple JSON document which describes your application, right? You state some basic stuff such as the application name, ID, things like that, number of instances. Most importantly, that's shown at the very bottom of the document. You tell it which Docker image exactly is supposed to be run in the environment. Then there is some other stuff. You can specify health checks, networking, etc. Once you have the document, you just issue a simple put or post request to the Marathon API, and you're pretty much set. The infrastructure takes care of everything else. Obviously, this little request is not done manually by developers. It's invoked as part of our deployment pipeline in TeamCity. This is how it looks like. This is just a screenshot of the Marathon UI. I don't know if you can see that, but this is an example of one of our applications running in 7 instances, I think. And if you look closely at the individual instances, you could see that it's actually spread over 3 or 4 machines in the cluster. This is pretty cool because if you happen to trip over a power cord and take one of the nodes down, Marathon along with Mesos take care of moving your, not moving, just reruns the instances on a different machine. But the thing is that you can handle these situations without any need for manual intervention. Once we had things like that, where we could just spin up new instances at will, it became natural for us to take advantage of scaling automatically. Now there are several solutions for Marathon and Mesos already, but most of them work on the basis of compute resources, right? For example, if you have a low RAM, you just spin up instances on some other node, etc. But we had to be able to base our autoscaling needs on the RabbitMQ queues. For example, when we have a lot of data flowing in, which is not constant, we need to spin up instances on demand. So we had to build our little tool ourselves, and it's very simple in its roots. It just checks the number of messages and adjusts the number of instances accordingly. Sorry.
Okay, so another thing that was pretty new for our team with cyber capture is that starting with this project, we actually started to be part of the on-call rotation. Up until now, the only people on call in Avast were like the infrastructure and CloudOps team. But starting with cyber capture, we were like the first developer team in Avast who actually was part of on-call. It was actually, there were actually 2 reasons why this must have happened. First reason is that it was really crucial that this system runs all the time, because whenever there's an outage on the backend, there's some amount of users running our application that just have their files locked and are waiting for the results. So that's one reason. And the other reason, from my point of view, was the microservices architecture. Because if we build the whole thing as one monolith, it would be much easier for someone else to run on call for it, because it's easier to understand. But if you have like 30 services with some dependencies in between them, it's harder for some outsider to understand what's going on when one of the services is not working. So the on-call thing was actually like a big issue in our team. When this came up, there was like weeks of discussions, because some people like didn't want to do that, and it's actually like obvious, because if you're part of on-call rotation you are on call during the weekend, you just can't go for a two-day hike into the woods, because you have to be near some stable internet connection, you have to be near your computer, and you have to wait if some incident come. But in the end, we actually agreed, because it was the right thing to do. So we started to be on call for this, and we actually had to learn how to be efficient while being on call. So the first thing that we actually realized is that it's very crucial to have a good monitoring in place, and also a good alerting. So for monitoring and alerting, we use Grafana that has alerting built in. So for example, as you can see on the screen, it's an example of one metric of one of our services. It actually shows number of messages consumed by that service. And it's obvious that around 10 a.m. there was some outage and the service stopped receiving the messages. And there was actually an alert triggered, which is obvious from the red dotted line. And the thing was fixed like several minutes later. So when talking about alerting, what's also important is to not have non-actionable alerts. Non-actionable alerts are alerts that are triggered and you just don't have to do anything, it just fixes itself after a few minutes. This is really, really bad, and it's for two reasons. First reason is that the person on call gets really frustrated because his or her pager goes on, goes off, goes on, goes off. That's one reason. And the other reason is that if you have such alerts, and if 30 times the alert fixes by itself, and the 31st time it's an actual problem, nobody really cares anymore because it's just ignored. So when there's an actual production incident, it's actually a very stressful thing for the person on call. So we try to make it easier for them. So we actually have two rules that we do. First rule is that for every alert that you create, you have to write the description. This description is sent along with the alert. So when an alert is triggered, and you're the person on call, you receive this description, and it can guide you how to fix the thing. The other thing is that we have one place where you can find links to monitoring and logs of that service, because usually there's a problem with one particular service. So to analyze that problem, you need to see the dashboards and you need to see the logs. So we have one central place where you can find this. For us, it's actually a README file in Git repository, but it just doesn't matter what it is. There just has to be one central place. So another thing that worked really well for us is to have one channel to which all the alerts are sent. So every time there's an alert, we receive like a screenshot from the monitoring directly into the channel. We can acknowledge the incident in PagerDuty or VictorOps directly from the Slack. And also what's important is that all the people from the team are in this channel. So if you're on call and you actually don't know how to solve this problem, you just ask people that are in the channel and then they might help you.
I'd like to conclude this with some thoughts on what we've been through the past year. So the system has grown into 34 services overall, out of which 14 are those analysis boxes, those services which do the heavy lifting of analyzing files which are flowing through our system. And just to illustrate, the system is pretty much still alive because new analysis boxes keep coming up almost every month because the research department is working on that all the time. We have confirmed for ourselves, and pretty much the hard way, that every new microservice does bring certain overhead. And you can do as much as you can to keep the overhead as low as possible. But it is so that more services you have, the more work you have on your hands. That's just something you can't get around. And we have found, and we've discussed this in this talk a few times, that it's absolutely essential to maintain consistency about everything. Everything has to be consistent, from logging to monitoring, what have you. And what we didn't do a good job at, to be honest, was to provide everyone the tools to be effective in this. We've invited a lot of other departments to participate in the system, people who work in different languages, but we didn't give them the right tools. So nowadays we do have some libraries which wrap those common conventions and rules which we require of everyone to adhere to. And I think we can go a step further. Alenka already talked about this by providing some scaffolding stuff or boilerplates so that everyone can be up to speed very quickly. Also, running our own cloud has been honestly quite a ride. It meant that everyone had to learn some new stuff. To be more concrete, Linux stuff. And if you weren't at yesterday's Robert Firek presentation about DevOps, I recommend to check it out from the recordings, because it describes pretty much exactly what we've been through. We had to cross the line from being just developers to get our hands dirty with some system engineering stuff as well. And initially we did build this internal cloud entirely in our team, but pretty soon we realized that it's by some standards it's a hobby project, and we need to make the whole setup more professional and reliable. So we seeked out help of the system engineering guys, and they helped us immensely to make it more stable. And yeah, so it worked well for us, but I wouldn't suggest this to everyone. I think we are a bit lucky in that as well. What's interesting is that it helped spark some new initiatives in the company. So as we speak, there's a team in Avast which is now designing a brand new company-wide internal cloud. It's probably not going to be Mesos Marathon, probably something else. That's still not set in stone. But the key point here is that we were kind of the pioneers. We have paid some price for that. But in the long run, I think it was beneficial to the whole company. But the most important takeaway I would like to put forward here is that this whole experience with microservices, it helped us to bring our team together a great deal, because otherwise we would never would be able to work in separate languages on the same stuff and have so much fun doing it. So if you're in that position as well, I think this might be the good approach to go with. So that's it from us. Thank you guys. And if you have any questions, just shoot or meet us later. And we would also love to hear, if you're doing microservices especially, love to hear your experiences, what you've been encountering and stuff like that. Thank you.